Okay, so you're welcome to the first lecture for STAT112. So, as I explained in the course outline, this set theory and counting processes will be the first topic to be treated under this course. Okay. Um, so you're welcome, and as you know, my name is Professor Richard Minka, your course lecturer for Group 1, in this case, the Actuarial Science students. So the purpose and learning outcomes, right? So for this particular lecture, we expect to equip students with the knowledge and skills, okay, or the skill set that you need to work with set theory and counting processes. And this will involve concepts, properties, and some applications in real world, right? Um, so by the end of this lecture or completion of this section of the course, you should be able to define and explain basic concepts in set theory. So, for example, when we say sample space or event, outcomes of a random variable, and so forth, what do they mean and how do you define them and explain them to a layman, right? Um, you should be able to also define and apply set operations, and these are things you've done at the SHS level: union, intersection, complement, difference, symmetric difference, and so forth. And also, you should be able to use Venn diagrams, okay, to analyze two set and three set problems, right? And then also to move on to apply the inclusion exclusion principle to count elements in overlapping sets. We'll also be talking about um, the counting processes, which will involve, for example, permutations and combinations. Okay, so how do you select with and without restrictions? Okay, when order matters, and when do you select with or without restrictions when order do not matter? And then we will solve some applied problems drawn from, let's say, Ghanaian and international context. So the idea here is not to go the way that you do in, let's say, SHS. We want you to understand it from basic principles, be able to explain whatever you are doing, even however complex it is, to a layman who has not done statistics at all. So that should be your goal in each of the topics we are going to treat. Should be able to explain it to yourself, to your colleague, and that's how you do it. You form, let's say, study group. So if you pick this concept, how are you explaining it to your colleagues? Maybe in a group of two, let's say three, okay, maximum 3 to 4 people. How do you explain? And they ask questions. How are you able to explain those concepts to them? Okay. Okay. So if you're able to do that, then it means that you understand. Then it means you understand the concept and the purpose, and then the learning outcomes you have, grabs most of them. All right. So, this lecture we are going to talk about some introduction to random experiment. Then we go on to set definitions and notations. Then the set operations and their properties, Venn diagrams and inclusion exclusion principles. Then counting processes or counting principles. Then we treat permutation combinations, and we'll end with some summary of some formulas that you need to know for this section. Okay, so what is a random experiment? Well, so in statistics, we do a lot with experiments, right? Now, these experiments, um, it mainly should be something that we, for example, know the outcome, right? So, let's say if I take a coin, when they are coming to play football match, if you are a referee, you don't want to be appear to be biased, right? Or so that you say this team should start from here and the other should be at the other side. Okay. In the past, let's say Kotoko and Hearts are playing together, and then you say Hearts and start from this side, or Kotoko start from this side. Then there will be chaos because some of them even believe in superstition like juju and so forth. That if I start from here, I'm going to lose and so forth, right? So FIFA then came out with a simple procedure that get a coin, let them choose which side they want, a head or a tail, toss it, okay, and then whoever if yours if you selected the head and the head turns up, then you win, and then you decide where to start from. So let's analyze it. The key thing, this is random, okay. The key thing is that we know the outcome. It when we toss the coin, it will either come a head will show up or a tail will show up. So that is known. What we don't know is what will happen. I mean, exactly which one will come up when you toss it. Okay, so that's a sort of experiment. All the weather conditions we grapple with every day. So sometimes let's say Ghana Meteorological Services will study the weather condition and tell you that there's a 70% chance of rain. Okay, then you take an umbrella, you go to let's say Accra, okay, Central Accra, and then the rain never comes. Okay, so in that case, you know that either it will rain or not, right? And just that you are not certain, even though there is a higher chance of rain coming, it did not. Okay, so that's it. So in random experiment, there are three key things that you can look out for. That the experiment can, what, in principle, be repeated under identical conditions. So, for example, the coin, if I'm tossing it vertically, I can toss it, several times like that. Then all the possible outcomes are known in advance. I know that a head or a tail will show up. I know that if I set off, it will rain or not, right? Then the exact outcome of any particular trial cannot be predicted with certainty. Okay, so that's it. So the rain is 70%. Even though there's a higher chance, there's still some uncertainty. Assigned to it. So basically, that's what we mean by random experiment. Okay, there are things like if you are adding, let's say 2 plus 4, you know that you always get 4. So that is deterministic. It is not a random experiment. Okay, if we check a die has 6 numbers, 1, 2, 3 up to, if we are playing what we call load, right? When you toss it, maybe you are interested in getting the 6 to start, but you realize that maybe you get 1, 2, 3, or 5. So you can't predict with certainty what really will come out when you throw, even though we know the possible outcomes. So that basically that's what we mean by random experiment. So some experiments, okay, rolling a die, tossing a coin, drawing a card from randomly from what, a well shuffled deck of 52 cards. Okay, then we have continuous measurement settings. So, for example, recording daily rain, daily high temperature in Accra on a randomly selected day, right? Okay, there are several values that we know, temperature values, just that we can't predict with certainty what the temperature will be this day or the day that selected. Okay, measuring the waiting time in minutes at a mobile kiosk in Medina Market, or you go to a bank, right? How long will it take for you to be served? Okay, by the time you finish, I mean, if you go the next time, it may not be the case because sometimes there may be network difficulties and so forth. So all those things are random stuff. Okay, but in the continuous case, you realize that you are recording something. It could be something, point something. They will not be whole numbers all the time, right? In the count case, if we are observing or discrete settings, you observe, for example, the daily number of loan applications received at a bank in Tema, right? That one, you cannot have 1.5 loan applications. It has to be 1, 2, 0, that nobody came, or 10, and so forth. So that's what we mean by count or discrete settings. If we are doing surveys, so remember in 111 we talked about surveys. When you have a population and then you take a part of it, you interview them or you take measurements from them, that's a survey. So selecting, for example, a student at random from UGLC 110 class of about 800 students and recording their GPA. All right. So I randomly select, I call it and ask you what is your GPA. That's a random thing, right? Okay. Noting whether randomly selected voter in Kumasi voted in the last election. Not every voter that registered or is on the electoral commission's register will vote. Okay, so that's a random thing. So basically, what in a nutshell, random does not mean no pattern, right? There may be a pattern, but the individual outcomes is uncertain, even if the long run behavior follows a law. Okay, so that key thing you should keep in mind, and of course the 3 key stuff we talked about in the classification of an experiment. Okay. Okay, so now we talk about outcomes, sample spaces, and events. All right. So by definition, an outcome, which is also referred to as a sample point, okay, is a single. It cannot be divided like result of a random experiment. So if I toss a coin, okay, the possible outcomes are head or a tail. So head is an outcome, and of course tail is an outcome. I throw a die, I'm expected to get 1, 2, 3 up to 6. 1 is an outcome, 2 is an outcome, 3 is an outcome, and so forth. So it must be a single point, right, in there. If I'm monitoring the weather condition, it's either rain or not. Okay, so raining is also 1 point. Okay, an outcome. No rain is also an outcome. Okay, or a sample point. Now, and then also sample space. So the sample space is all the set of all possible outcomes. So in the toss of the coin, you either get head or tail. So the set head, tail is a sample space, and sample space is also referred to as universal set. So in probability, we usually will refer to the universal set as sample space, but they are the same. Nothing changes. Okay. So in the case of the toss of the die, that is 1, 2, 3 up to what? 6. Okay, that's the sample space. Then event. So an event is any subset of the sample space or the universal set. Okay. So what are some of the events? We have the simple one. The simple event that contains exactly one outcome, which is just like your outcome, right? Contains exactly one outcome. So a head, it shows up. A tail shows up. It rains. You pass an exam. You get an A. That's an outcome. Just one single outcome. Then the compound event contains 2 or more outcomes. So the grades A and B plus together will now form a compound event, right? Okay. Or the set of even numbers. When you toss a die, that's let's say 2, 4, and 6. So that's a compound event. Then we have impossible event. The impossible events are the event that cannot occur, right? Never occurs. Okay, so I toss a coin, okay, and I want to get, let's say, a 5. That's not possible. A coin will either have a head or a tail, right? And so forth. Okay, or I toss a die and I want to get a value 10. That's not possible. Then we have certain events. So certain events are events that always occur. Okay, so for example, if I throw something and I want the sample space is a certain event. It always occurs. So to speak, you can also say that a certain event is not random, it's deterministic, because we know that it always occurs. Okay, so that's it. So these are some events, okay, and their classification. So even number, when you throw a die, will certainly be compound, right? Greater than 4 will also be compound. But getting a number 3 is a simple event, and getting a number greater than 6 is certainly an impossible event. So how many objects do we have in this, or members do we have in this set? That's our sample space. So the number is 6. Okay, so if you have the even number, that will be a set A. So that's a compound event. Okay, that's 2, 4, 6. Greater than 4 contains 2. That's also compound. The number 3, C, will be simple. And greater than 6, D, will just be odd and null set. Okay. Now the alternative for this, for the null set, let me try and write, is that you could also just write like that. Okay, so you have just the curly bracket, so that's also accepted. Okay, so we can use any of them. All right, now so that's an impossible event. So the focus of this is probability. So I now introduce this. As I said in lecture 2, we will be taking in-depth discussion of this. So the classical probability formula, we assume that the outcomes are equally likely, right? So when you are tossing a coin or a die and we say it is fair, then it means that 1, 2, 3 up to 6, each of them has an equal chance of being selected, right? Or showing up. If it is a coin, then head and tail have equal chance of what? Showing up, right? Now, so we will then define the probability of an event A as well, the number of members in that event divided by the total number in the sample space. So if we take A, the number of events in A is 3 because 2, 4, and 6. The number of events in the sample space is 6, so we have half. So what this means is that when we roll a die, then we have what? A 50% chance or 0.5% chance of what? Recording an even number. And similarly, we can get that of B, which is 2, right? C is 1/6, and probability of D is 0 because there is nothing in this event of getting a number greater than 6. So basically, that's a classical approach to probability. In lecture 2, we will be talking about the frequentist approach and then also the subjective approach to probability. But we'll do that later on. But with this, we should understand what we mean by probability. Okay. Now, if you look at this one, we will also talk about the axiomatic properties of probability. So, for example, because we are finding the event in that sample space, the maximum value you can get is when the event let's say A is out of the sample space, then you get 1, right? And we've also seen that the least you can get is when you have an empty set, which is 0. So we can say that probability will then be a value between 0 and 1, and so forth. So we will talk a lot about this as we move on. Okay. Now, so let's assume we tossed 2 fair coins, right? Head and tail. Then what are the possibilities? So the sample space will be that we can get a head and a head, okay, or a head shows up and tail shows up in the other one, or vice versa. Tail shows up in the first one, head shows up in the second one, or they all record what? Tails. So what is the number of members in this set? 4. Okay. So we can define the event, at least 1 head. If we have at least 1 head, then it means that it excludes only TT, right? So you have head, 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 tail, tail, head. Okay, so it means that the probability of A will be 3 out of 4. Both outcomes are the same, right? Then it must be head, head, and tail, tail. So that's half. Okay, first toss is a head, then you get head, head, or head, tail. Of course, that's also half. No heads will be what? Only TT. So the probability of D is what? 1 over 4. If we extend this to like tossing this either 3 coins or 1 coin 3 times, we can get HHH, HAT, and so forth till we TTT. So in this case, we have 8 observations, and we can get some events, some compound events, and get all of them, the probabilities. All right. So we can also look at certain outcomes, like let's say we toss the coin twice, but we define A that the sum equals 7. So it means that you need to go through all the sample space and get which numbers, the combination of numbers will give you 7. So for example, first die shows 1, and the second one is 6, it gives you 7. First one records a 2, the second one records a 5, it gives you what? A 7, and so forth, till we get 6 and 1. All right. So how many times can you get this? Well, 6. How many can you get it? Remember, you have like 6 times 6, so you get 36. So in all, 36 observations. B, doubles. So if it is double, then it means the first die and the second die should show the same number, which means 1 and 1, 2 and 2, 3 and 3, 4 and 4. So you get to 6 and 6, and that's also 6 out of 36. Sum exceeds 10, then it means it must be strictly 11 or 12, and that's it. And the sum equals 2, that can only be one case, so 1 out of 36. Okay, so each of these, we know we can get the outcomes. We can also get the probabilities and so forth. And one properties of probability is also complement. Okay, so if I have one side of that event, then the complement of that probability of the event not occurring will just be what? 1 over that. And we will look at this, as I said, later on in lecture 2 and actually prove some of these things. So here I won't waste my time. Okay. Now, so sample spaces. Sample spaces, we've seen that is what? The set of all possible outcomes of an experiment. Now, we are going to distinguish between discrete and continuous sample spaces. So the discrete ones, they arise as a result of some counting, sometimes a counting process, right? And that counting can result in a finite count, or it may be what? Countably infinite. But the key thing is that you can count, right? So for example, you toss a coin, that head and a tail, all right? We record, let's say, the number of times you throw, let's say, a die until you get a 6. Okay, in that case, it can be 1, 2, 3, 4, or never. You may toss it. That's a possibility that you never, obtain a 6, or you may obtain a 6 in the 100th time. Okay, or you stand. Let's say you want to construct a bridge. Okay, usually they have to check to know what is the load, what type of vehicles ply this road. Okay, so you can stand there and be counting the number of times you get, let's say, an articulated track. Okay, then it means that within a day you may not have one passing. That means 0 is part. There may be 1, there may be 2, there may be 3, or countably infinite. Okay, so that's a discrete sample space. So in the toss of a coin, that is finite. But if you are recording the number of trials, okay, till you get a 6, that may be what? Infinite. Okay. Then we can also talk about continuous. The continuous is usually an interval. And when you have an interval, it's difficult to know the actual number. So I can give you an interval that the numbers between 0 and 1, you can't list all of them. Okay, they are infinite. So usually continuous cases are, between an interval. And those are the values where you can get real numbers, so they are maybe point something and so forth. Okay, so in this example, we are going to classify each of these as either finite, whether it's discrete or continuous, and if it is discrete, whether it's countably finite or infinite. So the first one, you have calls to MTN call center per hour. So that the possibilities are 0, 1, 2, 3, and so forth. Right. So this will be discrete, but it's countably infinite. Right. Okay. Then we have X, the body weight in kilograms. So let's say we take our class, and the body weight, we know that is between 0 and 100. Right. That's continuous. Okay. And that's why for body weight, you may get point something and so forth. Okay. Then 0, 1, defective items in a batch of 5. Okay, so it's either 0, 1, 2, 3, or all the 5 items produced are all defective. So that's discrete, but it's finite. X and Y, random point in the first quadrant, X is greater than 0, Y is greater than 0. That's continuous case. Then you have K. K is a positive odd integer. Union 4 and 6. Okay. Then it means that this is discrete, but it is countably infinite. Okay. Because remember, this is union. So, where do you end? Okay. But if it was intersection, okay, then you are going to get, in this case, a null set, and that will be finite, right? Okay, so X is between 0 and infinity, lifetime in the years of light bulb, that's continuous. Okay, so you should be able to list examples on your own and be able to also classify it whether. Okay, so these are exercises you do in class, so please make sure you do some pre-analysis of it before you get to class, because you'll be asked to do this, okay, and discuss, okay, in class. So please take note of this. Okay. So I move on to talk about sets. So what is a set? Okay, and these are things you've done from your senior high schools. So we can define a set as what? A well-defined collection of what? Distinct objects. And these objects are called what? Elements or members. Okay. Usually we define the sets with capital letters, right? So you see set A, set B, and so forth. And the elements, you do that using the curly brackets or braces. Okay, so membership notation. If X is a member of A or an element of A, we write X with this symbol, which is X belongs to A. If X is not a member, you cross it out and then you have not a member of A. So there are some ways of defining or describing a set. Okay, so in the roster or the tabular form, we list all elements. So example, A is what? 2, 4, 6, and 8. Then we can also use what we call the set builder rule form. So in other words, in this case, I give what? A description, and you should be able to infer from this description what the set is, or the elements of the set, or the members of the set is. So A can also be said to be what? X is what? A positive even integer, less than 10, right? Okay, then that will also be the same as listing 2, 4, 6, and 8, all right? Okay, we can also talk about a Venn diagram, and we'll look at that later on. So, which is a pictorial representation, right, of this. Right. We can convert from one form to the other. So, for example, B, we say that B, S is such that X is a multiple of 3, and S is between 1 and 15. Then you should be able to list all of them. B will be 3, 6, up to what? 15. C, 1, 4, 6, 16, 24. Then it means that we can also define C as S is such that S is equal to N squared, where N is 1, 2, 3, up to 4, because those are squares of these numbers. Okay, so D is A, E, I, O, U, and we know that from our basic primary schools that this is what? X is a vowel, right, and so forth. All right, and so forth. So you should be able to convert between the forms whenever you are given. So types of sets. So we have the empty set, as I illustrated earlier, we define as that with a phi symbol, or it should be an empty set, right? So such sets do not contain any element. Then you have the universal set S or U, the set of all elements under consideration. The singleton set always contains only one element. Then finite set. A finite set is actually countable. They are limited. Infinite, we are counting up to infinity. So, for example, the set of natural numbers. Subset, the one on the left-hand side is a subset of the one on the right-hand side, which is B, is a subset of A. Then it means that every element in B can be found in A, but not vice versa, right? Okay. So the proper subset should be that B should not be equal to A. In other words, B should contain less element as A, right? And so forth. Then power set is a set of all subset of A. So written as N P of A, and that is 2 to the power the number in A. Okay. Then the equal set, if we say A is equal to B, then it means A is a subset of B, at the same time B is a subset of A simultaneously. So these are the types we look at. There are some examples here. So subset and power set. So if we let A be equal to 1, 2, 3, all subsets of A will be equal to 2 to the power 3, which is 8 of them. And you can list all of them from empty set up to this. Okay, so we can also get a power set, right? 2 to the power 3, which is 8. Subset checks 1 and 2 belongs to A, 1 and 4 belongs to A. It's false because we don't have any 4 in there, right? And so forth. So we can do some of these things and so forth. So counting proper subset will always be what? The power of the set minus 1. Okay, so we do all subsets except the A itself, and that's the proper subset. Okay, so section 2 exercises, I leave this with you as well to be discussed in class. Okay, and so forth. So please take note of it and try and get your own solutions to it before you get to class. Okay. There are some set operations, fundamental set operations that I need to talk about. So basically S is what? The universal set. Okay, and we are assuming that A, B, and AB are subset of S. So what do we mean by complement? Now, we say that A complement is X belonging to S such that each of these X is not in A. Is that okay? So, for example, I throw a die. The sample space is 1, 2, 3, 4, 5, 6. Then if A is even numbers, then the set A complement will be odd numbers. So the odd numbers will be all numbers belonging to S, which are not even numbers. So that's what this means. There are some facts concerning this, that if we find a complement again, then it of A complement, then it becomes A, right? I must also say that let me get out of this and say that other ways of representing complement will be A prime or A bar. Okay, so over here we may use any of these to represent complement, right? Okay, not only C alone. So please take note of that. Okay, then the union. So A union B will be that X belongs to A or X belongs to B. So in probability, the event that at least one of A, B, and B occurs. Okay, so if we are listing it, we list all elements in A, all elements in B. Of course, repetitions are just taken once, right? Then the intersection will be that if X belongs to A and X belongs to B, then we say they are what? There exists an intersection. So in probability, we say that event that both A and B occurs or simultaneously. Okay. Then we will also have what we call disjoint sets. In probability, we will refer to disjoint sets as mutually exclusive. Okay, so it will be used interchangeably. So if A and B are mutually exclusive or disjoint, then what we are saying is that their intersection is a null set. Now we can generalize this, okay, for several events. So AI intersection AJ is a null set for all I not equal to J, and this is important because if I is equal to J, then it's like the same event. So there's the same event intersection itself will give you the same event, which is A, and that will not qualify as disjoint. Okay. Then we also have set difference, right? Written A with the backslash B, which is that A intersection B complement. Okay. So this is such that X belongs to A and X does not belong to B. So the intersection of that is what we call the difference. Then we can also have the symmetric difference, which is symmetric difference B will be A, the set of the difference A intersection B complement union B intersection what? A complement. And that can also be written as A union B, right? Difference of A union B and A intersection B. So these can be said that elements in A or B, but not both. So that's what we mean by the symmetric difference. Okay, so some properties, commutativity, that A union B will be the same as what B union A. Then we can have associative, which is A union B union C, then it can be A union B union C. Okay, or even C union A, and then into bracket union C. It can be any way around. Okay, in the form, each of these union can also have this intersection form. So A intersection B would be the same as B intersection A, right? In the associative properties, A intersection B intersection C will also be A intersection into bracket B intersection C. Okay. Then the distributivity, that A intersection B union C can be A intersection B union or B intersection, so A intersection C, right? And so forth. And in the same way, you can have it in intersection from where the union comes before the intersection. Then, what do we mean by identity? That A union, a null set, is the same as A. And of course, A intersection, the sample space will give you A. We can have domination A union S is definitely S, and A intersection, then null set is also a null set. And then idempotency will be that A union A is A intersection A is A. We will look at this. And then the complement, A union A complement will give you what? The sample space. A intersection A complement will give you a null set. And the double complement will give you what? A. So these are very important, and we will use this in probability, so please take note of this. These are very important concepts that will help us in proving some concepts in probability. So for example, the complement, I can find the probability of A union A complement is equal to the probability of S. And union is plus, so it means that the probability of A plus probability of A complement is the same as the probability of the sample space. Remember, the probability of the sample space is 1, so definitely the probability of A complement will then be equal to 1 minus the probability of A. So these are very important concepts. We can also talk about the De Morgan's law, especially important in probability, that A union B complement is the same as A complement intersection B complement. And of course, we can do same with the intersection, that A intersection B complement is the same as A complement union B complement. So what does this mean? That neither A nor B occurs will be A union B complement, which is the same as A complement intersection B, and not both A and B will mean that A intersection B complement, and that will also give us A complement. So please take note of this, as we'll be using probability later on. So example, we have a set, the sample space 1 to 10. We have A, which is the numbers 1, 2, 3 up to 5. We have B, 3, 4, 5 up to 7, and then we have C, 5, 6, 7 up to 9. Now, so A union B will just combine the values. So you see 3, 4, 5 appears twice, but they are just counted once, right? A intersection B, we can do that. A complement, B complement, A minus B will just be what? 1 and 2, that is A intersection B complement. So B complement will be 1 and 2, and then what? 8 and 9. And those in A are just 1 and 2. So that's it. Then the B minus A will be B intersection A complement, and that gives us 7. So you can also the symmetric difference is also given. A union B complement through the De Morgan's law has also been done. So you can verify the De Morgan's law as that A complement intersection B complement, right, give 8, 9, 10. And that's the same as A union B complement in B. So yeah, we have it. And also the distributive, associative, we can do all that in there. Okay, integer intervals. So we have numbers between 2 and 15, and also 5 to 30. So union and intersection of the interval A union 2 will be that n belongs to real, and it should be between 2 and 30 because it's overlap. And also, you start from the minimum to the maximum. But the intersection B should start from where? 5, which means to be 6, right? Up to 15, less than 15, strictly less than 15. All right. So why? So A contains integers, right, from 2 up to, but not including what? 15. And A2 contains integers 6 up to, but not including 30. So the union spans 2 to just below 30, and also the intersection also spans in between these values. So we take an example on university subject enrollment. So a student selected from a Ghanaian university, let's say University of Ghana, we let M be the event that the student studies mathematics, student studies statistics, and C, computer science. So we can express each of these in set notations, right? Studies mathematics but not statistics. Studies at least one of the 3 subjects. Studies all 3 subjects. Okay. Studies exactly 1 subject, right? And so forth. And studies none of the 3 subjects by the Morgan's law. So you have to be able to express this in set notations, because when we are asking you probabilities, we are not going to give you the set. We will ask you what is the probability that you find, let's say, a student that studies mathematics but not statistics, right? And then you have to find it through this set mechanism. Okay. So D and E uses what? Mutually exclusive events, and also the De Morgan's law to three sets. Okay. Also, we apply the De Morgan's law in the context of health survey. So let H be patient has or hypertension, D patient has diabetes. Okay. So patient has neither condition will be H union D complement, which is the same as H complement intersection D complement. Patient does not have both H intersection D complement, right? That's H complement union D complement. Patient has hypertension or is not diabetic, so H union or D complement. So the De Morgan's law in probability will help us to find neither H nor D, right? And that's it. And this is complementary approach, which often simplify calculations of this. Okay. All right. So this is the third exercises to be done in class. Okay. And please take note of this before you get to class. Okay. Okay. So now I move on to talk about Venn diagrams. Remember the set representations. We've done all of them. Our last one is a Venn diagram. So a Venn diagram is a pictorial tool for representing sets and their relationship. Okay, so the conventions are that you have the universal set, which is the box, okay, or the rectangle. Then the set ABC are drawn circles inside the rectangle. Where they overlap is an intersection. Then you can, get, let's say B only, A only, A union B complement, and so forth. Complement of A, complement of B, and so forth. So we can identify all these sections in there, in it. So from this we do the inclusion exclusion principle, that the A union B, okay, if we want A union B, then it's like A union B. If we come back here, will be A, okay. We are going to count those in A only with A intersection B and then B only. If we are doing A and then B, it means we are going to count A intersection B twice, so you need to subtract one from it to help you get it. And that's the inclusion exclusion principle. So it means that the number in A union B will be the same as the number in A plus the number in B, but you count A intersection B twice, so you subtract one from it, and that gives you the value. And of course, you can get A intersection B from this. Okay. So mobile network subscribers, an example. So in a survey of 500 households, 320 subscribe to MTN, 250 to Telcel, and 120 to both. Now, the number of MTN Union Telcel users will then be what? 320, okay, plus 250, plus 250 minus the intersection, right? Those who use both, right? 120, so 450. Okay. So neither, if they do not use any of them, then it will be what? 500 minus 450. So this may be those using what? Airtel, Tigo, and so forth. Okay, investment club, an example is an investment club, 300 members, 104 invest in stock, 83 in bonds, 150 invest in stocks or bonds or both. How many invest in both? Okay, so here we need to turn it around and find the union, and that gives us 37, right, and so forth. Then there's a last example. So another example, as you are saying, is the investment club, and you can have this. So also take some university courses, 60 students, 35 take economics, 30 take geography, 15 take both, right? Okay. So you can have number that takes both, right? Okay. Those that take economics minus geography, we can find it. That's economics only. Geography minus economics, geography only. Neither this, and of course you can add all of them to get the 60 that we want. Okay. We can also do a case study, healthcare access in the Ghanaian district. So the setup, we have a community health survey in rural district covering 400 households. 240 access a health clinic, 180 access a pharmacy, and 80 use NIDA. Right now, so we can get a total using at least one of them. Okay, will be the total number of households minus those who use NIDA. Right, and this we can represent it in a Venn diagram like this. So 80 will be outside the this thing. We know 240 uses health clinic. So if you take those who use a clinic only plus those who use both, that should give you 240. The other one is also 180, right? A pharmacy. So the inclusion 180 like that. Okay. So we can find this. Now, so if we are able to draw this in a Venn diagram, what can we use it for? For example, if we are looking at policy, then you realize that there are healthcare gaps. So you see that more people use a clinic only, okay? But so within that area, you can then maybe get what? More pharmacy for them to be able to use. So what we are doing has practical applications in our everyday life, right? The Venn diagrams can be extended to 3 sets, okay? It's the same principle, nothing really changes except the addition of one more this thing, one more. So inclusion, exclusion, in the 3 set problem, the number of A union B union C will be the respective numbers for each group, then the intersections minus the intersection plus the main intersection, right, for all the 3 of them. And we can verify this quite easily. So an example is a UG subject survey. So 270 UG students, mathematics count 175, statistics, computer science 110, all 3 62. Those doing mathematics and statistics 135, mathematics and computer science 92, and then and so forth. So we can use this to get this and fill in the gaps in our in the Venn diagram. So please draw it and put all the values or you get in each part of this Venn diagram. There's another one on recreational activities. Quite simple. I want you to go through it and be able to draw this in a Venn diagram as well. There's also a case study on banking channel usage. So a bank surveyed 300 customers, those using mobile app, internet banking, ATM, 3 of them, right? So you get the number that are using mobile, the number that are using internet banking, and then ATM. Okay, we can get the intersections, those that use both, all of them, okay, or none. Okay, maybe some of them use checks and other stuff. Okay, so you can get all of this and be able to verify this. So this analysis guide banks in understanding which digital channels customers use and where to invest resources. Right. Okay. Okay. So these are the questions you need to complete as well in class for this lecture.